Hello everyone, welcome back to another tutorial. Today's topic is about friction. So let's start by defining what is the meaning of friction. Well, imagine that you have a box resting on a floor as shown in this figure, and you want to move or slide this box either by pushing or pulling the box. So we need a force P which is big enough to move the box. It's very natural to think this way. But we need to keep in mind that if P exceeds some force magnitude, you cannot apply a force of magnitude 0 to move the box, or magnitude maybe 1, maybe you need a magnitude of 10. So P has to exceed a certain magnitude in order for the box to move. Okay, so the question is, what happens to the box before and after reaching the required value of P? We know from Newton's second law, if we have a system of unbalanced forces, movement will occur, right? So which means in the case of static box, that is a box that doesn't move, we have a force or bunch of forces that is equal to in magnitude and opposite in direction to the force P, preventing the box from moving. Otherwise the box will keep moving in the direction of P. So there exists a force that resists this kind of movement. The only force we can think of is somehow located at the surface the box resting on, that meaning the ground. Okay, let's just assume it's in this position. The direction we know it's going to be opposite to P because it's resisting P, right? This is what is known as the frictional force. It's the frictional force by the surface. Now, we need to visualize this F. We cannot take it for granted. So let's go ahead and try to visualize it. So this is my box. And now I'm going to zoom in at this location. Going to zoom in very, very closely. So what can I see? Well, as you can see, the bottom of the box is not as smooth as it's, usually. You cannot see this by your naked eye, alright? Same thing goes for the surface. So let's just assume that, or let's just know for a fact that the bottom of the box and the top of the surface are not as smooth as they appear, alright? Now, if the box is to slide to the right, for example, it will be stopped at contact points shown in the figure below. You see these red dots. These are the contact points that will try to stop the box from moving to the right. Now, the bottom surface will exert forces R1, R2, R3, all the way to R9 to stop the motion of the box. Okay? The direction and magnitudes of these forces individually are impossible to pinpoint. Alright, because we have so many of them. Remember, I'm zooming on a macroscopic level. Alright? So, what is the trick here? The trick here is if we can resolve these forces into vertical and horizontal components, we can learn a lot about them. So, in this figure shown on the screen right now, I've taken all the forces, resisting forces, take them out of the image, put them in a white background so we can resolve them. Resolving the forces this way, and now I have two resolutions for each force. The vertical component, I will call it N, and the horizontal component, I will call it F. N, because it's normal force, it's perpendicular to the surface or the box, and F because it's a frictional force, as we will see it later on. So what can I do with this resolution? Well, let's look at the vertical component to start with, the ends. Okay, if I represent the ends component back in the box, what can I see? This is what I will see. Does it remind me of anything? Well, it looks like a distributed load with a load intensity of Qx. So if this load intensity was Qx, then the magnitude can be calculated of this load by integrating the function of this Qx, right, over L, and L is the length where the distributed load is acting. So acting at a point O somewhere at the bottom of the surface of the box is the resultant of the integration, or the magnitude, and this is the total normal force acting at the bottom of the box. If I follow the same logic, I can basically define or show that F can be represented on any point along the surface, just like in this figure. Alright, we need one more thing. We need to add the weight of the box to the figure to complete the free body diagram. So now we have the full body diagram of our problem. So what can we do with this body diagram? Alright, this is the body diagram. What can we find? Let's see. We can find F, we can find N, and we can find the location of point O. But how? Well, we can use our old trick, which is the equilibrium equations: summation of the forces in the x, summation of the forces in the y direction, and the summation of the moments about a point. Because we know that now that it's before sliding, just before sliding, this box is in equilibrium. All right. To apply the equilibrium, I need to define my coordinate system, and I need to define the distance x, which is the distance between point O to the line of action of W, and I need to define h, which is the height where the P is applied. Now I'm ready to take the summation of the forces and the summation of the moment. If I do the summation of the forces in the x, I will find that F equals P. So now I just solve for F. If I take the summation of the forces in the y, I can get the forces, or the normal force, which will equal to W. Now, applying the third equation, which is the summation of the moments, I will take the summation of the moments about point O, assuming that the positive moment acting counterclockwise. If I do this, I will basically say W multiplied by X minus P multiplied by H equals to 0, and I can solve for X, which is the location of point O, to be P H over W. Alright, now I was able, by just applying the equilibrium equations, I was able to find the value of F, the value of N, and the location of the point O. Now let's ask these questions. Question 1: can we always guarantee sliding? Is there any form of movement that can take place? Well, you can guarantee sliding in two cases. First, if the box was short, and the second, if the force is very close to the ground. That means H is very small. Alright? Question 2: how small should H be? Are there any other factors? Question 3: what about tall boxes? Well, let's take a look at this diagram. This is our free body diagram, and I'm going to use the fact that X equals PH over W. We notice the following. We see that if H and W are fixed, meaning the weight of the box doesn't change, and the force, or the height where I'm applying the force, is constant, the higher the force, the bigger the H. So H is going to get bigger and bigger, meaning it's going to go to the right. Alright, but it will reach a maximum value. The value of the value of X will reach a maximum value at the edge of the box. It cannot go beyond the box, beyond the edge of the box. And if it tends to go there by increasing P, that means I will not have sliding anymore. I will have a tip over. The box will tip over. So let's look at this tall box. Alright? If the box is about to tip over, meaning no sliding in this case, the position of point O is at the edge of the box, as shown in the tipping over is a rotation about a point O. Therefore, the normal force is located at the edge of the box. That's another way of looking at it. So from the moment equation, we know that the summation of the moments about point O should equal to 0. W multiplied by X minus P multiplied by H equals to 0. If I solve for X, it's going to be PH over W, and X, the maximum, is A over 2. So A over 2 is the maximum value of X. Now let's take a look at the coefficient of static friction. If a force is applied to the box, meaning non-zero force in this case, a frictional force will develop to resist the motion if the motion will take place, right? The forces developed in the box are. So let's take a look at the forces graphically. So let's assume we have a plot. On the x-axis we have P, on the y-axis we have F. And now I'm going to increase P going from 0 all the way up. Alright? If I increase P, F increases until it reaches a static frictional force called Fs. It's going to look something like this. Alright? And Fs in this case equals N multiplied by mu S, and mu S is what we call the coefficient of static friction. The reason it's static, or the reason it's called coefficient of static friction, I still don't have any movement within that range. P going from 0 all the way to where it reaches a value of Fs, no movement takes place. So I'm at the edge of movement. If I keep increasing P, I will have a movement. Now Fs is not Fs anymore, it's called Fk. It's the kinematic frictional force, and it's gonna look something like this, and it's usually I believe it's always less than Fs, and Fk equals the normal force multiplied by mu k, and mu k is the coefficient of kinetic friction. By looking at this graph, I see that if the box moves, we're not in static mode anymore. That means we cannot use mu s, we should use mu k. But since we are doing with static problems, we'll always use mu s. So what do we conclude from this? Well, if the motion sliding is to take place, just tiny bit, Fs will equal N multiplied by mu s. If tip over is to take place, Fs does not equal N times mu s. Alright? So what problems to expect? Well, what type of problems should worry about? Well, one of the problem will ask you probably, what is the minimum force to move a box on a horizontal surface? The other problem can ask you a minimum force to move a box on an inclined surface. One problem can ask you for the minimum force to hold the box from sliding downwards on an inclined surface. A problem will ask you for a minimum angle where for a surface to cause sliding. So you have a surface, an inclined surface with a box, a crate on top, and you are able to increase the angle of this inclined surface. So at what angle the box will start sliding, or the crate can start sliding. One of the most famous problems asking you applying this force at this location in a box or system of boxes, will it slide or will it tip over? Okay, so in the next slides we will go over an example for each type of these problems. So for the first example, we have this box is being pulled by a force P, and the force P is not horizontal, it has an angle theta, which is okay. Just trying to make it a little bit interesting, that's all. So the question says determine the minimum required force P that will cause the box to move. Given W is 1,000 pounds, mu s is 0.7, and theta is 30 degrees. So what can we do about this? First, define the coordinate system and draw the free body diagram. That's the key to all the problems in friction. Probably all the problems in statics, but for friction, start by defining the coordinate system and draw the free body diagram. So this is my coordinate system, and this is the box. I'm gonna apply I'm gonna impose or draw the free body diagram now. First, I have to resolve this force into components. Horizontal component being P cosine theta, and the vertical component being P sine theta. I'm gonna add the W, the weight, Fs, which is the opposite direction of the movement or the potential movement, and at some location that I don't really care where the location is right now, at the bottom, pointing upwards because it's a normal force. Now I have to check are all my forces within the coordinate system, are they all vertical and horizontal, nothing inclined, nothing has an angle? Yes, I have 1, 2, 3, 4, 5 forces. Fine, so I'm ready to apply the equilibrium equation. But first I have to keep in mind that if movement is to occur, that means Fs in this case equals n mu s. So whenever I see in my formulation an Fs, I'll substitute it with n mu s. So let's apply the equilibrium equations. Summation of the forces in the x will give me P cosine theta minus Fs, which is n mu s, equals to 0, and summation of the forces in the y equals to 0, giving me n minus W plus P sine theta, and that's equal to 0. Looking at these equations, I know W, I know theta. The only two unknowns I don't know are P and N. And two equations, two unknowns, solvable. I will solve just for P now. Solving for P will lead that to P equals 575.65 pounds. So the minimum required force P that will cause the box to move is 575.65 pounds. Now let's take a look at the second example. We have this crate on an inclined surface with an inclination of 30 degrees being pushed by a horizontal force, alright, P. I'm asked to determine the minimum required force P that will cause the crate to move up. I'm given the mass. Notice I'm given the mass. But from the mass I can calculate W, which is W equals mg, mass times the gravitational constant, or the gravitational acceleration. And I'm given mu s equals 0.25, and from the figure I'm given theta, which is equal to 30 degrees. Okay, what is the key to the solution? Define the coordinate system, draw the free body diagram. So this is my problem. This is the coordinate system I'm going to use. This coordinate, I mean, you can use the conventional coordinate system, x to the right, y to going up, but I find it easier for me to visualize this problem. In this problem, it doesn't really matter what coordinate system or how you define a coordinate system, but it will make life easier for me if I define it this way. So I'm gonna apply here. I'm gonna have the frictional force Fs, and I'm gonna have a normal force. See, the reason I chose the coordinate system to be this way, I wanted N and Fs to be along the coordinate system I chose. So any other force that's not along the coordinate system I chose, I have to resolve into component that goes along, or into components that go along the x and y direction I'm defining here. So W is always pointing downwards, and now I have to resolve the W into two components as shown, and of course the P has to be resolved into two components as shown on the figure. From that, I'm ready to apply my equilibrium equations. But again, from the question we see that cause the crate to move, so movement is there, or in other words, sliding is there. Fs should equal n mu s. So whenever you see an Fs in the formulation, it has to be replaced by n mu s. So applying the equilibrium equations, I will get summation of the forces of the x equals p cosine theta minus n mu s, which is Fs, minus mg sine theta, mg being w, equals to 0. And if I do the summation of the forces in the y direction, I will get n minus mg cosine theta minus p sine theta equals to 0. Again, looking at these two equations, I don't know p, I don't know n, I know everything else, so I have two equations, two unknowns. I can solve for p, and I will get p equals, in this case, 474 newtons. Okay, let's look at another example. Well, it looks the same, but looking at the wording of the question, determine the minimum required force P to hold the crate from sliding. So the crate has a tendency to slide, and I'm trying to hold it back. So the movement is downward. Solution: movement is downward. Again, I will define the coordinate system and draw the free body diagram. This is my problem. This is my coordinate system. Notice here that the only difference between this problem and the previous problem is the direction of Fs. Since the crate is trying to slide down, the friction should go up. And again, resolving the forces into two components, so I can use the summation of the forces, the x, y, and not the summation of the moments in this case. So sliding is about to occur. F equals n mu s. Applying the equilibrium equation, I will have summation of the forces, the x equals to 0, p cosine theta plus n mu s, which is Fs, minus mg sine theta equal to 0, and in the y direction, n minus mg cosine theta minus p sine theta equals to 0. Solving for P, I will have P of 140 newtons. Now let's take a look at the fourth example. I'm having this crate on an unknown angle, inclined surface with an unknown angle. I'm asking what is the angle theta at which the crate will start sliding. So imagine the crate is on a horizontal surface, and I'm lifting or trying to make it with an angle with the horizon, and of course at a certain angle the crate will start sliding. I want to know exactly at what angle will the crate start sliding. Alright, movement again is downward. Define coordinate system, draw free body diagram. This is the problem. This is my coordinate system. Now this is my free body diagram. Since the movement is going to be downward, Fs should go upward, and W is always pointing down. Remember, no P in this case. So now I have to resolve W into two components, as shown. Then, since movement is about to occur, Fs equals n mu s, and now I can apply the equilibrium equations. Summation of the forces of the x equal to 0. I will have n mu s, which is Fs, minus w sine theta should equal to 0, and in the y direction n minus w cosine theta equals 0. Solving for theta in this case because well, I have two equations with two unknowns, n and w, I mean n and theta, but I'm interested in theta. We find that theta is the tan inverse of mu s, and we notice here that theta does not depend on the weight of the crate. Alright, now for a more challenging example. It's going to be our final example for this presentation. So I'm giving two boxes on top of each other as shown on the figure with these dimensions. These two boxes are identical. Alright, what am I given here? I'm given that W1 equals W2 equals 200 pounds, meaning the box 1 and box 2 are both 200 pounds exact weight. Mu12 equals 0.8, which is the coefficients of static friction. It's 0.8 between box 1 and 2, that's the subscript 1, 2, and mu2g is between box 2 and the ground, it's 0.5. So what is the question? What is the minimum force P that will cause motion? That's it. Well, we see that the problem statement did not specify the type of motion expected for this system. Will there be any sliding? Will there be any tip over? Is the top box will slide alone? Is the whole system will tip over? I mean, so many possibilities, right? So all possibilities should be studied, alright? And the case with the minimum required load will govern, and we will explain more about that. But now let's think about the possibilities. How many movements can we expect from this system? But here's our strategy. Get the possibilities, calculate the load that will cause each movement, and the minimum of the loads will be our case. Okay, this is the first scenario. P is applied, box 1 will slide. Alright, possible. Now the second scenario is P is applied, but box 1 is, box 1 tips over. That's also possible. Now the third possibility is the two boxes slide. And finally the fourth, both boxes tip over. So we have 4 problems to work with. That's why it's a little bit challenging. But again, take it step by step, slowly, and we should be able to do them. Let's take a look at first case. Box 1 slides. Alright, again, define coordinate system and draw the free body diagram. In this problem, the coordinate system is easy. Alright, it's the regular XY. The coordinate system is in the regular XY direction. So this is the box, these are the forces. All I need to do now is apply the equilibrium equation. Since there is a sliding, the point O where the normal force act doesn't have to be at the end. Alright, so applying the summation of the forces, I can solve for P, which will equal Fs, which will equal N mu12. Summation of the forces in the Y will equal to 0, of course. N will equal W. Alright, so P equals Fs, and Fs equals N mu12. But we don't know N, but from the second equation we know that N equals W, so it's W mu12 equals 200 multiplied by 0.8 is equal, that will equal to 160 pounds. So the first case, if it will happen, it will need 160 pounds, meaning the first box or box 1 slides. Now let's take a look at the second case. Box 1 tips over, so we have a tipping over now. Alright, now I have to put the N force at the edge because there is tip over, no movement, no sliding, and in this case, because there is tip over, I need to include the moment equation. But let's see how can we simplify things. With the system shown, with the forces, can do the summation of the forces in the X, but notice here that P equals Fs, but Fs does not equal N mu12 because we don't have any sliding. In the Y direction equals 0, N equals W. But I cannot use these two equations by themselves. They don't provide that much information for me to solve the problem. Here I can use the third equation, which is the summation of the moments about point O equals to 0. So it's W multiplied by 3, which is the width of the box, over 2. Remember, it's A over 2. That's the arm, moment arm, minus P multiplied by H. H in this case is 1. So 200 multiplied by 3 over 2 minus P multiplied by 1. I solve for P. In this case, P equals 300 pounds. So P2 for the second case, which is the case where the first box tips over, is 300 pounds. Now, third case. Well, the third case says that both boxes slide. Alright, so this is the free body diagram, and summation of the forces in the X equals to 0, P equals Fs equals N mu12. In this case, this one should be mu2g. I'm sorry, there is a typo here. This one should be mu2g. Alright? Summation of the force in the Fy equals to 0. Now P equals Fs equals N mu2g. I corrected it here. And N equals W from the second equation. So we have W mu2g. Now I have W, I have mu2g. W in this case is 400 because the weight of both boxes are sliding. So it's 200 plus 200, which is 400, multiplied by 0.5, which is mu2g, will give me 200 pounds. So P3 is 200 pounds. Now the third case, if both boxes tip over. Well, we've seen that applying the summation of the forces in the X and Y direction for the second case did not get us any results. So we had to use the moment equation. It was the moment equation that got us results for the tip over case of box 1. Now we will skip the summation of the forces and we go directly to the moment equation. Summation of the moment about point O should equal 0. So W multiplied by 3 over 2 minus P multiplied by H. Again, 400 W now, because we are talking about two boxes tipping over, multiplied by 3 over 2 minus P multiplied by H. H in this case is 5. So P4 is 120 pounds. So these are the 4 cases or 4 scenarios that can take place for this system. Now I need to compare the 4 results. Comparing results, I see P1 is 160, P2 is 300, P3 is 200, P4 is 120. Of course, 120 will govern. Why is that? You're applying the force starting from 0. You will never reach 160 or 200 or 300 before reaching 120. So when you imagine yourself applying the force 0, 10, 20, 30 all the way to 119. Alright? Once you hit 120, you'll have a tip over of the two boxes and the other solutions are not valid anymore. You will not have a sliding of two boxes, you will not have a sliding of the top box, and you will not have a tip over of the top box. Alright, so we can say that the two boxes will tip over when a force of 120 is applied. Okay, so that's it. I hope you learned something today, and I'll see you in future tutorials. Thank you.